In section 3.4, a lot of things that we've been going over the last few days are going to come together for solving linear programming problems. And let me just tell you what linear programming is. It's a method of finding a maximum or a minimum value of a function that satisfies a given set of conditions called constraints. And a constraint is an inequality in a linear programming problem. A feasible region is the solution set of the inequalities. When you look at the graph, at your graph, it's the overlapping region, the overlapping shaded region. And in 3.3, you identified overlapping shaded regions. So now we're going to use that information to make some decisions on maximum and minimum values of functions. So the objective function is the equation that's used to find the best combination of values in order to maximize or minimize the function. The objective function may have a minimum, maximum, neither or both, depending on the feasible or the shaded region. So if you look at this table, and here you may not be able to see it real well on the video, so I kind of highlighted here. This is not closed. This is bounded, so it's all closed. These two are unbounded, so it's open here and it's also open here. If it's closed, the area or the region is closed, the feasible region, then you have a minimum and a maximum. If it's open, you have either a minimum or a maximum, but not both. Okay, the vertex principle of linear programming says that if an objective function has a maximum or minimum, it must, and you need to insert the word occur here, at one or more of the vertices of the feasible or the shaded region. So instead of going into more detail with the vocabulary, we're going to just go ahead and work out a linear programming problem. So phrases like less than, greater than, those are indicators that you have a constraint or an inequality, because the constraints will be inequalities. Non-inequality information, so anything that doesn't say greater than, less than, and so on, is going to be an indication that you'll have an objective function. So here is a linear programming problem. We have some constraints, or you could think of them as restrictions, and several different ones, and we want to know the best combination of players to send to camp with these constraints. So I'm underlining or color coding here. We know that it's $75 for each advanced player and $50 for each intermediate, and she can spend no more than $13,250. Also, she wants to send at least 60 or more advanced than intermediate players, and in addition to that, she wants to make sure she has a minimum of 80 advanced players. Okay, so if you try to sit down and make all the different combinations of advanced and intermediate players and try to get the most, you could be doing this forever. So linear programming can help you do that in a more time-efficient manner. Okay, first you want to identify your variables and label your axes. So we're going to let X indicate our advanced players, and we're going to let Y indicate that, or Y represent our intermediate players. All right, now we're going to list the important information. So basically I'm just pulling things out of here and writing them down. So I know that I have $75 for each advanced. I know that I have $50 for each intermediate, and with both of these together, I can't spend any more than $13,250. So that no more than indicates an inequality. The next one I have, it says at least 60 more advanced than intermediate. So that's another thing I need to come up with an inequality for. A minimum, so that would be at least 80 advanced players. And then we're going to throw these two in because we can't have negative people. So you know that, but when you're graphing, you need to close that your feasible region in. So we know that the advanced players have to be greater than or equal to 0, and the intermediate players have to be greater than or equal to 0. Okay, now Once you have all that information listed, we need to write the constraints or the inequalities, and we'll get them from this information up here. So we kind of already set this one up. We have 75x plus 50y is less than or equal to 250. And we want we want 60 more advanced players than intermediate. So if I know, I'm going to slide this over just a little bit. I have intermediate players, and if I add 60 to that, that means my advanced are going to be greater than or equal to y plus 60. So because it says at least, so we want at least 60 more advanced than intermediate. Okay, so that's our next inequality. The next one, we want a minimum of 80 advanced. So advanced is represented by x, so we want x greater than or equal to 80. And then again, we want the x is greater than or equal to y is greater than or equal to 0. Okay, so we're going to go ahead and graph all these. So what I want to do first is label my axes. Let me slide this up just a little bit so you can see the x. We're going to label the axes with x being advanced players, and the y is going to be intermediate. Okay, now we need to graph this line. So if I do x and y intercepts, if I cover up the y, then my x-intercept is going to be at 176 2/3. So over here, I'm just going to go x equals 176 2/3. And I cover up my y. And when I cover up my y, it's going to be, cover up my x to find my y, it's going to be y equals 265. All right, so now we need to graph that line. And not a bad idea to put this in slope-intercept form as well, because we want to get an accurate point, and if we just kind of draw a line, bam, our ruler may be a little bit off. So I am going to put a point down here at 176, but I am going to put this in slope-intercept form. So this in slope-intercept form would be y is less than or equal to -3/2 x plus 265. Okay, so that's actually what I'm graphing. So I'm going to use both of these to get a real accurate line here. So I'm going to go down 3 and over 2. So one, 2, 3 over 2. 1, 2, 3 over 2. 1, 2, 3 over 2. 1, 2, 3, 2. 2, 3 over 2. 1, 2, 3 over 2. Okay, then we're going to go down. Okay, so it looks like when I line this up, I have a much better go for my line, because that 176 2/3 is kind of hard to graph, but when I go down and over, it makes it a little bit easier. Okay, so we have this one graphed, and now this one, if I put that in slope-intercept form, I have y is less than or equal to x minus 60. So y is less than or equal to x minus 60. Okay, my y-intercept is at -60. So I don't have any negative values here. So what I could do is I can look for my x-intercept. So my x-intercept would be here at 60. And I know I have a slope of 1. So from there I can go up 1 over 1. Now it doesn't matter that these are going by 10, because if I go up 10 and over 10, it's 1. So up 1 over 1. And I'm putting lots of points here just because, if you can see right here, that's a point of intersection of those two lines. So the reason why I'm putting so many points is because it's really important where your vertices are when you're doing linear programming. Okay, so I'm going to, draw a line here. Now, I'm going back to this line right here because I want to, I put that in slope intercept form and it says less than, so I'm going to shade this line. Okay, and now I have this line right here. And it says less than, so I'm going to shade below the line. Okay, so now I have this triangle region here, but we still have a couple of more to graph. So this says x is greater than or equal to 80. So here's my 80. And numbers are greater than 80 this side. Okay, so number, I went over a little bit there. But remember, we went where all of the regions come together. Okay, so that's going to happen right here. So what I'm going to do is I'm going to just darken this region. Or my shape so far. And then we have x is greater than or equal to 0. So here is 0, and I'm going to shade up this way. So it's everything this way, greater than or equal to 0. So this is the y. Actually, the y is greater than or equal to 0. And then I also have the x greater than or equal to 0. Okay, so now here's my shape. It closed it in with the y is greater than or equal to 0. And you do need to do that because if you don't do y is greater than or equal to 0, then it's unbounded down here, even though we don't have the negatives there. So what I'm going to do now, what's really important on my graph are the vertices, because the minimum and maximum values are going to occur at your vertices, that combination. Okay, so we have, if I go around my figure here, we have a ordered pair at 80, 0. We have another one at 80, 20. And another one at, let's see, what's that? 130, 70. And then another one here at 176 2/3. 0. Okay, now, I kind of jumped over this objective function here. So our objective is to see how many advanced and how many intermediate players we can get. So the most that we can get by staying underneath all of these constraints. So what we do now, the max is going to happen again at one of these vertices. So we're going to take, this will be our x and y. Our objective function says that we take the x plus y. So here we do 80 plus 0, and actually this, just make this a blank here, is going to be 80. Then we're going to add x plus y, so 80 plus 20 is going to give us 100. And then 130 plus 70 is going to be 200. And this is going to be 176 2/3 plus 0, so 176 2/3. Now we look down here and we look for the largest value. The largest value is going to happen, largest value is 200, and that happens when we have 130 advanced and 70 intermediate. So if we identify the maximum and the minimum values, the maximum is going to be 200, and the minimum is going to be 80. So now what you do, because we want the maximum, we find the maximum number, and then we go back and say what that combination represents. So the maximum is represented by 130 advanced and 70 intermediate.